The answer was absolutely.
The M109A6 Paladin may look like its predecessor, the M109. But with cutting-edge technology, the U.S. Army considers today's Paladin a new weapon system, a cannon with a brain.
The heart of the Paladin system is its integrated onboard fire control system, comprised of the inertial navigation system, the GPS, the onboard ballistic computer and weapons controller, and its ability to process digital communications.
With a touch of a button, and without soldiers ever leaving the vehicle, this howitzer will automatically take aim and fire. Because of the built-in navigation and automatic fire control systems, the crew doesn't have to see the target to hit it. When the Paladin receives a fire mission with designated coordinates, the onboard computer calculates a firing solution and automatically unlocks and points the cannon so the crew can fire the first projectile within 60 seconds.
Because of the responsiveness of the fires and the accuracy of the Paladin, made it a very lethal weapon. I could shoot a target as long as it's at least 500 meters away from me. So from 500 meters to 30 Ks, we can shoot it.
Today's Paladin brings two strategic capabilities to the modern field artillery. First, responsiveness.
Responsiveness is incredibly important for the soldiers that are supported by cannon fires. When the maneuver elements or the infantrymen call for fire support, the Paladin system can provide that in a near real-time environment. Earlier versions of M109s could not provide that timely, responsive fires.
And the second, survivability. On the earlier M109s, it took up to 15 minutes to respond to fire orders because soldiers had to exit the vehicles to manually find their position on the battlefield, putting their lives at risk. The soldiers never have to leave the new Paladin. It shoots and scoots. It fires quickly and moves at 40 miles an hour, greatly reducing exposure to enemy fire.
With the Paladin, if I've got to reload a howitzer to keep its combat load, the only people who really are on the ground is the ammo guys. It's alleviated a lot of checks.
The Paladin can shoot 4 100-pound rounds a minute, accommodating a wide variety of munitions, including cluster bombs and high-explosive rounds. But this smart cannon will soon be firing a smart bomb. Currently being developed by Raytheon Missile Systems is the precision-guided weapon Excalibur. Excalibur will be the Army's first artillery projectile guided by GPS.
As the round exits the cannon itself, it begins to receive and track satellite emissions from the GPS satellites. Prior to launch, it's been provided with the target information for the target of interest for that mission. It can be detonated above the ground for more area-type targets, or it can actually be detonated as it comes in contact with a target.
The 40-pound Excalibur will be able to steer around objects to locate its target at distances within 50 kilometers and can be programmed to change its trajectory in mid-flight. The Excalibur is intended for urban environments where there's risk of collateral damage.
So you can take out the target without taking out the building, the school bus, the civilians that are in the same block that the target set is in.
The deployment of the Excalibur will mark the first time smart weapons will be used in cannon warfare.
It will revolutionize cannon artillery. It just came a little slower than bombs because of the environment it needs to survive in coming out of the cannon tube.
The Excalibur will be distributed to the Army in 2006. It will make the Paladin a superweapon, one of the most lethal incarnations of a battlefield technology that has its origins in the 13th century. The Chinese were the first to cram gunpowder, which was invented in the 9th century, into a long tube, load it with an iron projectile, and thus create the first cannon.
There wasn't a grand revolution once gunpowder was invented. They were used as fireworks, they were used as loud, scary kind of noisemakers, but not really effective siege weapons. But by about the mid-13th century, first quarter of the 14th century, gunpowder and cannon make its way to Europe.
The purpose of early cannons was principally as a siege weapon. In an effort for some princes to consolidate power, they had to have a way to reduce those tall, standing, high-walled castles. And the way to do that is to drag out these siege cannons, put them in place, and very methodically pelt the base of these ancient castles and cause them to collapse.
These siege battles tended to last for months, if not years, allowing gunners time to literally build cannons on the battlefield. Even with all this practice, producing cannons in the 13th and 14th centuries was a mysterious mix of science and art.
The folks that ran those things were considered a little different, and they were very clannish. They stuck together. The guns are extremely expensive, so they are very personalized. They took great pride in them. And as you look at the guns, you can see that they carry the emblems of either the nobleman or the king. Some of the guns that you'll see have dolphins, sea dragons, all those things that are, at the time, considered good omens, good luck charms.
Interestingly, the first cannon makers were bell makers, because they understood the technology of working with metal.
They would have a sand mold made and then pour the liquid metal in and cast the cannon that whole way so that it would cool from the outside in. And then when it was finished, you broke the mold apart and you had just a solid tube. What you did then was they took a metal borer and bored out the center of the tube to make your actual gun tube, so that you would have that firing channel.
Over the next 2 centuries, bronze, which was lighter and easier to move around the battlefield than iron, came to dominate the cannon industry. This despite the fact that iron cannons were 10 times cheaper to produce than bronze. The first person to fully utilize lightweight cannons on the battlefield was the 16th century Swedish monarch, Gustavus Adolphus.
He lightened up the guns so that the guns could move along with the infantry and provide fire support to the infantry on the battlefield, which was a big advance also.
Cannoneers would fire a cannon by placing the cannonball and a powder charge inside a flannel casing. The cannoneer would then muzzle load the explosive. Once that happened, the cannoneer would take a goose quill full of powder and stick it through an opening at the base of the cannon, igniting the charge. By the late 14th century, cannons started firing exploding shells. Made of stone or bronze, the shells were joined together by hoops and exploded by use of a primitive fuse. They were usually filled with an incendiary mixture and mostly used against forts. Most cannons could fire a stone or iron ball roughly 1,000 yards. But since the cannon bores were smooth, the aim wasn't always true. A smooth bore can't control the projectile because the shell is just pushed through the barrel. Rifle-bored cannons produced a stabilizing spin on the shell. Once the fuse was ignited, the gas pressure inside the cannon barrel expanded and secured the shell inside the rifling grooves, improving its accuracy and range.
Rifling originally had little to do with accuracy. The rifling was simply a groove cut through the cannon that allowed the powder to collect. It was a place to collect the spent powder to get it out of the way of the bore, and then they would clean it out and ream it out. Discovered eventually that with the right twist, it made it more accurate.
Large cannons saw their first dominant role surface in the 1588 Spanish Armada. The British and Spanish fleets battled for almost 2 weeks in the English Channel. Each side had roughly 40 warships, but it was the size of the British cannons that eventually overwhelmed the Spanish fleet. Naval battles would never be the same, as large cannons became the weapon of choice on the high seas. Because of their mobility, smaller cannons prevailed on the battlefield. And in the winter of 1775, a Massachusetts bookstore owner altered the course of the Revolutionary War. Henry Knox recovered 50 British cannons and brought them to Boston from the captured Fort Ticonderoga, forcing the British to retreat from Boston. Several months later, of course, the colonists declared their independence from Great Britain. Following their success in the Revolutionary War, cannons played a larger role in the Mexican-American War. But it wasn't until 1854 that a British hydraulic engineer named William Armstrong solved the problem of gas leaks and made a major advancement in improving accuracy. He developed a process that would heat and shrink the barrels over the cannons to improve the strength in the area where the greatest internal pressure occurred. Armstrong and other cannon makers coupled this advance with breech loading, and finally, they rifle bored their cannons.
The problem up until the 19th century was that cannon were made out of bronze, and if you make something out of bronze, you can't rifle it. So you needed something hard.
Iron cannons had always been cheaper to produce than bronze, and now with the problem of leaks solved, they regained favor. By the 19th century, the Industrial Revolution allowed foundry workers and metallurgists to jumpstart a cannon production boom. Probably the most significant foundry was the West Point Foundry in Cold Springs, New York. It was one of 4 sites selected by President James Madison following the War of 1812 to produce cannons for the U.S. This foundry produced the majority of cannons used by the Union Army in the Civil War. As is often the case, war pushed the technological envelope, and the Civil War era propelled cannon technology on several fronts.
The first of these, obviously, was smokeless powder. You need to have a propellant that when it sends that projectile out of the tube, doesn't give away the position of the tube. The second invention, of course, was the recoil cylinder. Remember, before the invention of the recoil cylinder, when a gun fired, the whole gun moved back. And you had to roll the gun back in battery and put it back into position before you could shoot it again. Well, when that happened, you were never assured that the tube was back in the same spot each time. And it wasn't until you had the ability to have the gun recoil down a slide and move back into position after each round that you were able to do that. The third invention was the invention of really effective and reliable fuses.
Fuses had been around for almost 150 years by the time the Civil War started. The fuses were wooden tubes, several inches long, that were rammed into the projectile and lit right before firing. The fuse would launch the projectile as well as detonate the shell over the target area. Having the fuse detonate at the desired time was always troublesome. This was solved with the invention of the percussion fuse, which detonated upon impact. By the end of the 19th century, cannons would become the centerpiece of battlefield artillery. Out of this elevated role would come larger weapons to wreak havoc on unsuspecting civilians, as well as terrified soldiers. At the beginning of World War I, cannons had a commanding presence on the battlefield. They were now being mass-produced. But while their numbers increased, their accuracy did not. Countries from all over the world wanted quicker firing, more accurate cannons to gain the upper hand. But without effective recoil systems, accuracy wouldn't improve. Unfortunately, established recoil systems didn't allow cannons to keep their position once fired. Large springs were the best method used in cannon recoil systems, but even they wore out quickly due to the excessive force generated by these cannons. With the world watching, the French unveiled a historic recoil system that changed the way cannons were built.
They came up with what they call the hydro-pneumatic system. In fact, this is what they put on their famous French 75, and it was their secret weapon.
Where other cannons used springs, the French 75 used cylinders. One filled with oil, the other filled with nitrogen. When fired, the cylinder filled with nitrogen would compress. This actually pushed the cannon back into battery, making it ready to fire again. The French 75 was the forerunner of modern field artillery. Its hydro-pneumatic system also allowed the cannon to return to its original position gently, decreasing the wear and tear on the cannon.
And they could do up to 12 rounds a minute out of the French 75. They used to say they would have 1 in the gun, 6 in the air when they were really firing fast.
cannon weighed 2,700 pounds, was about 18 feet long, almost 10 feet wide, stood 6 feet high, and was protected by a gun shield. The 16-pound projectiles were breech-loaded and had a range of roughly 7,500 yards.
You got a real killer now on the battlefield. And in the First World War, that's going to become very, very, very important.
The French 75's recoil system set off an international game of how'd they do that?
In fact, in World War I, when they brought it over to America, we couldn't take the gun apart to find out how it worked because it was a French national secret.
It leaked out. There's no way you can keep something like that under wraps. And pretty soon, all Europe's armies are going to have something like the French 75.
This new cannon was the standard bearer in the early days of World War I. But as the war moved into the trenches, the French 75 became less effective. In fact, the French 75, like all cannons that launched projectiles with high trajectories, fired over the heads of soldiers who had burrowed into the ground. The Germans were the first to counteract this problem. They built the biggest cannons to date, two 42-centimeter howitzers called Big Bertha that smashed the fort at Liège, Belgium in August 1914.
No one had ever seen that before, that you could take a siege gun, which was in effect a big siege mortar, and smash these very modern forts.
The whole function was to have it go up to about 20,000 feet, turn over and come down and penetrate deeply into the earth.
Named for the daughter of the Krupp Gun Foundry founder, the Big Bertha was able to launch 1,800-pound shells at its enemy. Because of its weight, Big Bertha had to be transported piecemeal behind 5 motor tractors and assembled on site by a crane.
The Germans brought her forward, and she was one of the first motorized artillery units. It took them about a day to emplace the battery, and then a day to get the range settled in. But once they did, they smashed each fort in turn and destroyed them all.
But there was a problem. Firing Big Bertha damaged its recoil system to such a degree that she could only fire a few times a day. Nevertheless, Big Bertha was a precursor to weapons that would become a staple on the front lines of World War I.
Railroad guns are pretty effective in World War I in that they are big. And remember, the front in the First World War is fixed, so it doesn't move very far. And when you bring up a 14-inch gun that fires a projectile that weighs 1,800 pounds, that's pretty effective. When an 1,800-pound round lands on top of your head, you know it.
Several armies developed similar weapons to Big Bertha, causing the Germans to up the ante by producing an even bigger cannon.
From the Big Bertha, Krupp then developed what they called the Paris gun. And this was an attempt by the Germans to sow confusion and panic in the French capital in 1917.
At 142 tons, the Paris gun more than tripled the weight of Big Bertha. She fired a 150-pound shell more than 75 miles. The Paris gun had an unprecedented 110-foot-long barrel. From March to July 1918, the Paris gun was hidden in the forest of Crépy, on the outskirts of Paris, and aimed at the city. Once fired, the French had no idea what hit them.
In fact, when it was first fired into Paris, the French thought a gasworks had blown up. They didn't realize that they were being shelled. The secondary thing was, well, maybe they were being bombed from the air. Such a high-flying Zeppelin, perhaps, that they couldn't see it. After a while, though, it became apparent they were being shelled.
This was one of the first guns that actually got something up into the upper atmosphere. And so it would get up there and then just kind of skip on the way down.
The interesting thing about the Paris gun was that it was so big that it had to have a superstructure above the gun, because when the gun fired, it whipped.
As the Allies pushed Germany on other fronts, however, the Germans had to rethink the usefulness of the cumbersome and costly Paris gun.
They ceased firing the Paris gun, took it back to Krupp, and dismantled it.
While the Paris gun met its demise, large cannons on ships and in harbor defenses were duking it out throughout the war. Naval and coastal cannons fought on equal terms until coastal artillery seized the upper hand with the development of a weapon that seemingly vanished as quickly as it appeared.
The advantage of a disappearing gun is that if your enemy is restricted to flat trajectory fire, as most naval weapons were at the time of their introduction, then the disappearing gun is raised up over an earthen concrete parapet, fired, then the force of its recoil carries it back under or behind that parapet.
This worked because the enemy only saw the cannon for the few seconds it was firing, so he couldn't get a fix on it. Also, the parapet protected the cannon. But naval cannons eventually answered this problem.
The demise of disappearing carriages was really brought about by the improvement in technology to naval artillery that allowed them to indulge in high trajectory fire.
The Germans would benefit from that technology. Their love of large cannons would show itself again following World War I. They would begin plans for a killing machine that would make the Paris gun look like a pea shooter. As World War II began, Germany continued to push the envelope in its development of large cannons. While Big Bertha and the Paris gun were only destructive in limited instances, the Germans still felt large railway cannons were a key part of their arsenal.
During World War II, the Germans developed a gun called Dora. It was an 800-millimeter gun. It took 3,000 men 6 weeks to emplace the gun. It had a 500-man crew to fire the gun. It had a major general for a gun captain. Here is a tremendous amount of assets that you have to pour into a weapon that is that big.
Dora weighed in at roughly 1,350 tons, by far the heaviest cannon ever produced. It was so huge that, like Big Bertha, it had to be moved by rail in sections and erected on site. Dora stood an imposing 38 feet high, was 23 feet wide, and 141 feet long. Its shell, filled with high explosives, could weigh up to 7 tons and would leave cities in rubble. Propelled by a charge weighing almost 2 tons by itself, this massive projectile traveled as far as 24 miles to reach its target.
It and another large gun called Gustav were used at the siege of Sevastopol in Russia. And that was their job, was to break up large concrete formations and fortifications. They did the job well, but aircraft using large bombs could probably have done just as well and would have freed a lot more men and a lot more technology, a lot more manufacturing capability that went into building them.
The German army always had this love of giantism. And so whenever they had an opportunity to reduce a fortress, they would haul up these monstrous works of art like Dora and Gustav in the siege of Sevastopol.
While Germany was preoccupied with big guns, the Allies took a different approach to gaining cannon supremacy. In 1943, after a 3-year trial and error period, the Allies perfected the proximity fuse, an anti-aircraft weapon that enhanced the lethality of cannon artillery.
What the proximity fuse did was you put a radio transmitter into the nose of the round. The transmitter puts out a signal, and when the round gets a return signal off the target, it would detonate the round.
The fuse first saw action with the U.S. Navy in the Pacific Theater. It worked so well that Army personnel wanted the fuse to support field troops, in addition to attacking German aircraft.
During the Battle of the Bulge, the United States is in trouble. So what's done is they take that proximity fuse and they give it to the field artillery. And with field artillery, now you can fire that round and it will burst 30 meters above the ground every time.
Detonating over the ground increased the potency of the charge because the area hit was larger than one struck by a traditional shell. Cannon artillery equipped with a proximity fuse was also used by the Navy's big guns in the Pacific. The USS Iowa class of naval warships. 4 Iowa-class ships were built. These battleships were almost 900 feet long and equipped with 9 mammoth 16-inch diameter bore cannons that were some of the largest ever on a warship. These Iowas were known as swimming pool makers because of the 200-foot diameter craters produced by their shells, the largest weighing 2,700 pounds. The Iowas contained a fire direction system consisting of gyroscopes and an unheard-of onboard computing system.
The Aiken relay calculator allowed the Navy to quickly compute and compensate for errors and ranges, to be able to determine what a projectile would do. It was a natural marriage of the complexities of naval gunfire to the computer age.
Nicknamed the Mark I, Aiken's computer allowed the USS Iowa-class battleships to fire and hit targets 23 nautical miles, about 26.5 statute miles away, with almost pinpoint accuracy. With aircraft carriers and the Iowa-class leading the way, the United States replaced Great Britain as Queen of the Seas. Unfortunately for the U.S., unmatched firepower on the water didn't translate to coast artillery preeminence. New technology forced the U.S. to reconsider its commitment to cannon-based harbor defenses.
It was evident that in the U.S. that as far as we were concerned, aircraft and surface-to-surface guided missiles were going to be the weapons of the future that would take the place of coast artillery. And so our heavy coast artillery didn't last a decade past World War II.
By 1949, all the coastal artillery defenses were abandoned or disbanded, leaving only an assortment of iron monuments, like this one, at the U.S. Army Ordnance Museum. Even as one branch of military ceased wielding cannons, new possibilities opened up for cannons, and the wrath they would unleash on the world. The devastation in Japan that ended World War II altered the landscape in cannon technology, as scientists and military officials pondered how best to utilize cannons in the second half of the 20th century. Harnessing nuclear power was a global concern in the years following World War II. In the early 50s, the U.S. military worked with the U.S. Atomic Energy Commission to develop an atomic cannon.
They're trying to get an atomic weapon on the battlefield. Seems like a good idea at the time. The problem of getting an atomic weapon on the battlefield, a tactical nuclear weapon, was that you could only shrink the warhead down so small. The smallest they could get it was about 11 inches, 280 millimeter. And so atomic Annie comes into effect. A huge gun. It fired a 15 kiloton projectile 25 miles.
Atomic Annie's nuclear warhead packed an astounding 15,000-ton charge. 10 of these warheads would equal the force that decimated Hiroshima. Atomic Annie was 40 feet long and weighed 85 tons. But what set her apart from other cannons was the new wrinkle of having debilitating nuclear capability. On March 25, 1953, in Frenchman Flats, Nevada, an atomic cannon was test-fired for the first time in history. Following its successful test firing, a handful of atomic Annies were built and sent around the world.
It gave the Army something to use in the nuclear race. That the Army could say, see, we too have nuclear capability. We have this very big gun that will fire a nuclear shell. Because you've got to remember, 1950s, there was talk of not even needing armies anymore at all. You would just need the Air Force to come over, drop the nuclear bomb on the enemy, and they, then you need a few soldiers to march in and, mop up. So the Army was looking at a way of staying in the game. And by having this nuclear shell, it was able to do so.
If you really go out to Fort Sill and look at Atomic Annie, it is essentially a railroad gun that sits down on a firing base rather than stays on the railroad tracks. And rather than having railroad trucks underneath of it and pulled by an engine, it had two large motor power units that snagged onto it, picked it up, and towed it around.
Atomic Annie's nuclear feature was just one of its never-before-seen qualities. Scientists needed to develop a system that could sustain the force of a cannon that fired nuclear warheads. So they improved upon a turn-of-the-century idea.
Atomic Annie does have a double recoil system, and what that means is there is recoil, the normal recoil system you see in a lot of guns that come this way, but it also has one underneath so that it slides this way. And the reason for that is it softens the recoil of that thing so that it can be rapidly fired again if needed.
The big problem with Atomic Annie and the guns like her was the same problem the Germans had. A battery was 2 guns. Normally a battery is 6, but this is a large battery with 2 guns that takes about a day to emplace. Your range is 20 miles. And in fluid warfare, sometimes, they're going to move faster than that.
The other problem was, of course, the Soviets were a lot of things, but they weren't stupid. So they always had this thing targeted. Anywhere it went, they knew where it was.
These problems proved too much to overcome, and Atomic Annie went the way of Big Bertha, the Paris gun, and the Dora gun. This Atomic Annie now rests at the U.S. Army Ordnance Museum in Aberdeen, Maryland. In fact, during the early 50s, it was thought cannons and field armies in general would be unnecessary, since you could launch missiles and keep soldiers out of harm's way.
So the missiles were what phased out Atomic Annie, because they were quicker to set up, they could go farther, they could hit harder, they were about as accurate. So it was as far as you could go with artillery and atomic weapons at the same time.
In order to compete against rockets and missiles, developers increased the mobility and accuracy of cannons so that they could remain a viable option on the battlefield. The Korean and Vietnam Wars were the first opportunities for cannons to prove they could still get the job done.
The big advance made in Vietnam was a thing called the fire base, where the engineers could go out with a little bulldozer and very quickly clear away a clearing in the jungle. And then you could fly in guns and support an infantry operation well within the artillery FAM, so that you never had infantry outside the range of artillery. So the mobility of the helicopter was exploited to carry in guns, build these fire bases, fire away.
But the real issue of Vietnam was that the mobility and the adaptiveness that was demanded to survive caused the American forces, to include the artillery, to get out of a mindset that at least occurred since World War I of a linear battlefield.
With Vietnam's ever-changing front line and hilly terrain, smaller, lighter, more mobile cannons were necessary. To help combat Vietnam's unique landscape, the U.S. developed a new cannon. In 1966, the M102, a self-propelled 105mm cannon, was first deployed.
Well, the M102 was another 105 howitzer, but it had a base plate that was staked into the ground and allowed the gun to traverse 360 degrees. Another obvious advantage, it was designed to be sling-loaded under helicopters, and it was lighter. Therefore, it gave you a more deployable system.
Vietnam showed military leaders that wars were fluid events, and you needed artillery that would best match the war environment. It also showed them that cannons and their projectiles needed to be more adaptable.
And of course, Secret of that was the invention of precision munitions. When artillery becomes as precise as smart bombs, then we'll find ourselves into this new age of precision firepower, precision cannons.
Mobile, lightweight, and now equipped with precision projectiles, cannons reclaimed a commanding role in the battlefield. But at least one more world leader would fall victim to his unabiding obsession with large cannons. Before he gained international recognition as a Middle East strongman, former Iraqi leader Saddam Hussein was intrigued by the idea of having a supergun, a cannon so large that he could fire it into space. In 1989, Hussein met a Canadian-born astrophysicist named Gerald Bull, and their joint vision began to take shape. Ever the bully, Hussein wanted to aim his supergun at his Israeli neighbors.
The problem with that was, well, several problems. One, it was fixed into position. So how many rounds are you going to be able to fire before the Israeli Air Force, which is a very good Air Force, finds the gun and bombs it into about 8 million pieces?
Because the supergun was so large and shrouded in secrecy, it was shipped in sections from England, where it was built, to Iraq under the pretense of being petrochemical pipes. When complete, the cannon would be a nearly 200-yard-long supergun, firing a 600-kilogram projectile, roughly 700 miles. The components for the cannon came from factories in England, Spain, Holland, and Switzerland. Unfortunately for Hussein, British customs agents seized the final 8 sections of the supergun in November 1990, before it could be finished. While Saddam Hussein won't be harboring dreams of a supergun anytime soon, the United States continues to upgrade its cannon technology. New cannons for possible future wars will be produced in the same place they've been produced since 1813, Watervliet Arsenal near Albany, New York. Watervliet is the oldest continuously active arsenal in the United States. It is the only arsenal in the country making large caliber cannons for today's military.
We're not here to build and produce a piece of metal that just goes and sits somewhere. We're here to build a cannon, an artillery piece that will work, that will protect us and our soldiers, and also not malfunction.
The process of manufacturing today's cannons is a continuation of the art form started in the 13th century.
The rotary forge is set up so that you take a preform of this gunmetal steel, which is maybe 8–10 feet long. We take that and we put it into an induction furnace that heats that preform up to about 2,000, 2,100 degrees.
After it's taken out of the furnace, the barrel travels on a conveyor belt toward the rotary forge.
This huge cannon will begin to turn and move into the jaws of the rotary forge. The rotary forge has 4 large hammers, and those hammers are controlled by a computer control room.
The size of the cannon barrel determines how much force the hammers will use to shape the barrel.
Anytime you heat up steel, you lose some of its properties. So what you have to do is heat it up again and instantly cool it. You'll put it through this annealing process, which, if you cool it instantly, it returns all of its metal properties to it.
This entire process takes about 15 minutes, down from the 15 hours it took only 20 years ago. The U.S. Navy is also taking advantage of improvements in cannon technology. The newly commissioned USS Winston Churchill is the first destroyer equipped with airgun, the extended range guided munition system. It's a rocket-assisted 5-inch, 120-pound projectile with a range of 60 miles. This range is an increase by more than 50% over current destroyers. While that's impressive, field cannons are even more imposing as they become more lethal and autonomous. The high-tech capabilities of today's Paladin M109A6 have proven that. But despite the Paladin's innovative automatic firing system and its future compatibility with precision-guided weapons, such as the Excalibur XM982, there is still some talk in military circles about cannons becoming artillery dinosaurs.
In this contest to determine which is the optimum weapon to use for fire support in the future, whether it's going to be a rocket-based or a cannon-based system, it really comes down to what system best supports the changing nature of war. The precision revolution and the information revolution all are going to change the way armies fight. Battlefield of, say, 2015 or 2020 is going to be a enormously more lethal battlefield where armies will be spread over greater and greater distances, and weapons, because of their precision, are going to be used more sparingly in the future.
However clean the battlefield of the future may or may not become, at some level, war is likely to remain a hands-on business in which victory can only